Hi everybody. So let us start with module number 4, fracture, fatigue and fit. Basically, these are failure of material related phenomena. So under working condition, material fails. So to have better design, right, we must know these various fracture or phenomena or failure phenomena for material. So, in case of fracture, it is actually failure of material under load into two or more phases. So, there are two types of fractures. So, first is ductile fracture and second is brittle. So, this plot uh, explains how different materials behave differently under load. So, this typical stress versus strain plot. For ductile material, right? This is called ductile material. Failure at B dash starts from A, ends at B dash, and another graph is for brittle material. It starts from A and ends at B. So in case of ductile fracture, when ductile material has gradually increasing tensile stress, it behaves elastically up to yield stress, and then plastic deformation occurs with the failure of material. So let me show same plot and explain. So in case of ductile mode of fracture, suppose we start from point A, and when we start applying load, right? So as stress increases, strain also increases, and they have linear relation. So this is called as a elastic limit. Okay, up to this point. So elastic limit means here there is no breaking of bond. Here there is no breaking of bond. Elastic energy or potential energy stored in a bond utilizes. So at this point, if we remove the stress, what will happen? Metal will bring back without any. Okay, so that is what's stated in the statement. So as we increase load gradually, right, by applying tensile stress, for example, so it behaves elastically up to this yield point. It is called an elastic yield. But after this yield point, if we keep on increasing stress, what will happen? There will be plastic deformation. Okay, and material will fail at point B dash. So, due to this plastic deformation, we call such materials as ductile. Okay, so this is what the case with the all ductile materials, or this fracture at this point B that is called the ductile fracture. Okay, so material is not failed at elastic limit, not failed at yield point, but uh, plastic deformation is continued and failure occurs at point B. So this is ductile fracture or ductile failure. Now another category of material called as a brittle material, or a brittle fracture. So in this case, when tensile load, the stress is applied on material, right? Stress stress is applied on material, strain is also increased. Okay, so they are linear relation. But at this point, at point B, at elastic limit itself, right, material fails. Material fails. Okay. There is no plastic region. Okay. So such materials are called as a brittle material, and failure is called as a brittle fracture. So this brittle fracture is usually observed in case of glass or ceramics, and this ductile fracture is usually observed in case of metals. Okay, so these are the two modes of fracture or failure of metal. Ductile fracture, where we observe plastic deformation after elastic limit. And second is brittle fracture, where there is no plastic deformation, so no ductility. Okay, so same thing is shown. These are actual pictures of failure of materials. So picture A is cup and cone fracture in aluminum. This is ductile fracture. Okay, which will be observed in case of aluminum. Cup and cone. So after failure, you can see cup like shape and this is cone like shape. Initially, this sample was intact. Two pieces were joined and they were subjected to tensile loading. Okay, suppose this is what the initial case. Okay, and tensile loading is applied. So what will happen due to tensile loading? So material will start uh, okay, breaking or damaging at this point. So initially holes are produced, then crack is propagated or crack is initiated. It is then propagated in this deep data and material eventually fails. Okay, in this cup and cone kind of unit. Okay. So this is observed in case of metals and metals. Okay. Now the second is a brittle fracture. There is no cup and cone kind of failure. So this is called the brittle fracture. Okay. And this is example of mild steel. Then this fracture phenomena is or can be better understood with the help of Griffith theory. So here we have to see derivation for critical stress. Griffith's work was motivated by two contradictory facts. So he observed see, two contradictory phenomena in case of glass. Okay. So what are those? The stress needed to fracture bulk glass is around 100 megapascal or maybe or you can say 1500 psi. So what he did, he subjected bulk glass to tensile loads. Tensile. So what he observed, stress required to for fraction of a bulk glass is 100 MPa, just 100 MPa. But theoretically, theoretically, in case of same bulk glass, stress needed for breaking of atomic bonds of glass is approximately 10,000 MPa or this is 50 right? So there is a huge difference between practical stress required for failure of bulk glass and theoretical stress. Okay, so he was surprised why it is so. Practically, bond strength is this, and sorry, theoretically bond strength is this, and why practically the glass is undergoing failure earlier. Okay, so why this is so? So he started chasing the problem and he come to the derivation of critical stress. So according to Griffith, so what he proposed is there are possibility of having micro cracks inside the material, okay, while it's non-critical. So material is never perfect. There are defects. Okay. So theoretical calculation of glass or any material, okay, it's based on consideration that there is no defect at all. But when we go on manufacturing any component out of material, micro cracks are always there. So what he said, so there are micro cracks in metals that cause local concentration of stress to values high enough to propagate the crack and eventually fracture of metal excess. Okay. So what he suggested is in any metal, while it's processing, micro cracks are generated. So when we apply any stress, okay, so failure occurs earlier than theoretical prediction. So that earlier failure, okay, of that material is because of presence of micro cracks. And those micro cracks they leads to uh, enhanced local concentration of stress. So stress is doubled or tripled sometimes, okay, due to presence of micro cracks and material fails or fractures earlier. So, so he proposed this model. So consider an electrical crack of length 2c, yeah, in simple cubic structure of unit thickness under tensile stress. So he considered this cubic structure, simple cubic structure, like this structure. So he considered elliptical crack with length is 2c. So we suppose this crack is already there during its manufacture. Okay, and thickness of the structure is its thickness is suppose 1 unit thickness and crack load is 2c and tensile stress applied is suppose sigma. Okay, so the tensile loading spread from both the directions. So what will happen is this. Okay, how crack will be produced in that material. Okay, okay. So when bond breaks, now when we apply tensile loading, these bonds will start breaking. These are the bonds, and we know that these bonds store potential energy. So when this bond breaks under tensile loading, there will be release of elastic energy, which is stored in a bond. Okay? So when this bond break, elastic energy stored, okay, elastic means potential energy stored will be released. And after breaking, what will happen? Bond breaking of bonds creates new surfaces. Two surfaces are created, upper surface and lower surface. Then surface energy, one more type of energy comes into picture. So crack can only be propagated if released energy is sufficient to create new surface. Okay, this is also Griffith criteria. Okay, when crack will be propagated, if this released energy is sufficient to create new surface, if after breaking of the bond, whatever energy is released, if that energy is sufficient to create new surfaces, then and then the crack will be propagated further. That is what his observation. Then accordingly he derived, okay, one formula for critical stress to initiate or propagate action. So first formula we need to write is total elastic energy per unit volume, that is UE, when crack introduced. Okay. That total elastic energy per unit volume is UE is equal to pi by 4 into 2c square, 2c bracket, 2c square into T. T is the thickness. Okay. So this part into half of the stress. Okay, half of the stress applied into E, strand created in the material into E. So this is well known formula for total elastic energy per unit volume. Okay, so this is our equation 1. Okay. So here everything is stated. U is total elastic energy per unit volume. Sigma is stress applied. E is the strand created. E is Young's modulus. Okay, that is from latter. Okay. T is the unit thickness of the plant, C is the length of plant. Now we know that modulus of elasticity, E of elastic modulus, Young's modulus, E is equal to stress is strain. We have already studied. Okay, elastic means stress. Okay, now you can say stress is directly equal to strain. So stress is equal to elastic modulus into strain that we have already studied. So stress is sigma and strain is E into your equation number 2. Now put value of strain E from equation 2 into equation 1. Means we take value of E. E will be what? E will be sigma upon modulus. Okay, E will come down. This strength will come down, sigma upon E. So that I will substitute in this in the place of E. Okay. So what I will get? So energy will be remaining terms will remain as it is. 5 by 4 into 2c square into 3 into half into sigma. As it is, you need to write. Only you have to change this E. E will be replaced by sigma by modulus E. Okay, using this relation. Interchange as it is. Okay. So I will simplify this. What I will get is this 2 4 4 will get cancelled. So pi into c square. T is 1 unit thickness into now this sigma square 2 get cancelled divided by T. So this is what is the simplification. So in short what I have is this pi into c square into sigma square upon E. Okay. So in equation 1 above, 2 at the end is for upper and lower surface. So this expression is given for this 2 appear over here or in the equation number 1. This 2 is because of what? We have two surfaces. When crack is generated, we have upper surface and lower. That is what? 2. Multiplied. Now second part is total energy U sigma. Total energy U sigma. So what is that total energy? The crack formation process produces two new surfaces that I will show in diagram of this. Okay, the crack formation produces upper surface and lower surface. Okay, and the total energy, total surface energy, okay, altogether will be U sigma, and that is theoretical energy 4 into gamma into C, where gamma is specific surface and theoretical. Okay, so, and now, so third step will be the energy change during the formation of crack. Okay. Now, the energy change during the event of formation of crack. What is that? Delta. That is supposed to be delta U. The total energy will be total surface energy, which is U sigma 4 gamma C, okay, plus elastic energy release that we have written in the step 1. Okay. So addition of these two. So total surface energy is 4 gamma C over here and elastic energy release we have calculated in the last slide. But that is taken negative. Negative sign because that indicates elastic energy stored in the material is released. Okay, energy release means it is considered as a negative loss of energy. Okay, as the crack forms. So delta U is equal to 4 gamma C, so minus, okay, plus into minus pi C square sigma square upon E. Now we are interested in calculation of critical fracture stress. So stress at which fracture of a failure of material takes place. Okay, initiated in material. So that critical fracture stress may be obtained by differentiating with respect to C and equating it to 0. Means this is what equation we have for delta U. Okay. So we have to take derivative of delta U with respect to C and equate that derivative with 0. Okay, so that means d delta u by dc is equal to 0. Okay. Now delta u is this quantity. So we have the derivative of this with respect to c. So that derivative will be this. D by dc, the cell equation is equal to 0. Now we know see dc by dc will be 1. So we will get 4 gamma for this term, 4 gamma minus c square derivative is 2c. So that is what we can evaluate 2 pi c sigma square by is equal to 0. Okay. So it is simplified. 4 gamma is equal to this. Okay. So gamma is equal to this. We will get gamma square first and then we will get square root. So ultimately what we have is sigma is equal to or critical stress or fracture. Okay. Sigma is equal to square root of 2 gamma into E divided by pi into C. Okay, so this is about the derivation for critical stress required for fracture of. Okay. Now, that was a uh, Griffith theory, or Griffith theory, this is called the critical stress. But that was applicable to only brittle metal like glass. But in engineering, we use several metals and alloys visually. So, Orwell made modifications here. The Orwell, what he did, he added plastic deformation concept. See, in case of brittle material, there is no plastic deformation. Material fails at yield point only, at elastic limit only. There is no plastic deformation. Okay, no ductility. But in case of metals and alloys, which are our majority of engineering materials, they show plastic deformation due to dislocation unit. Okay, so they are not brittle actually, they are ductile. So that part should be added, and that is called as Orovon's modifier. Griffith theory only applies to perfectly brittle metal like a glass. Okay, but in crystalline materials, where fracture is apparently visible, there is plastic deformation. That is what I just said. There is a plastic deformation next to fracture. So, Orowan thus modified the equation, including plastic inhibition. He just added this term P, plastic work required to propagate the current. That's all. Otherwise, the formula derived by Griffith and Orowan is remains same. So what he did, sigma of A S is actual fractal square. Okay, in general is equal to square root of 2e. So in the previous formula there was only gamma. Okay, so he inserted gamma plus P. P factor means plastic deformation will be found. Plastic work required to propagate. Okay, so gamma plus P divided by pi. Okay, so P is plastic required to propagate. So this is called a 401 modification.